You click a link. A full web page appears. Colors, images, text, interactive buttons. The whole thing visible within a second or two. But that single click triggered a cascade of at least a dozen distinct technical operations, each one depending on the previous, running across networks, servers, and your own device simultaneously. Nothing about a web page loading is simple. It only feels that way. Most people picture a web page as a single file on a single server delivered when you ask. The reality is messier. A typical modern web page makes dozens to hundreds of separate requests for different resources. HTML from one server, CSS from another, JavaScript bundles from a CDN, images from object storage, fonts from a font provider, analytics from a third-party script. Your browser assembles all of it into one coherent view. The first step after a click is translating the URL's domain name into an IP address. Your browser checks its own cache first, then the operating system cache, then the router's cache, then a recursive DNS resolver. Each cache layer avoids a full lookup. When the resolver does have to work, it queries root name servers, then TLD servers, then the authoritative name server for that domain. All of this typically resolves in under 100 milliseconds. With an IP address in hand, your browser opens a TCP connection. This is a three-step handshake. The browser sends a SYN packet, the server replies with SYN-ACK, the browser confirms with ACK. Only then can data flow. On a connection to a server 100 milliseconds away, this handshake alone takes 100 milliseconds round trip before a single byte of web content moves. For any HTTPS connection, after TCP comes a TLS handshake. The browser and server negotiate a cipher suite. The server sends its certificate, the browser verifies it against a trusted certificate authority, and they exchange keys to establish an encrypted session. Modern TLS 1.3 has cut this to a single round trip in the happy path, roughly having the overhead compared to older versions. Now the browser sends an HTTP GET request. This is a structured text message specifying the URL, the HTTP version, accepted content types, cookies, and a dozen other headers. The server reads the request, routes it through potentially a load balancer, an application server, a database query, and a cache layer, then assembles the response and sends back an HTTP response with status code 200 and the HTML in the body. The browser receives HTML and immediately starts parsing it, even before the full document arrives. It builds the document object model, a tree structure representing every element on the page. When the parser hits a script tag without the async or defer attribute, it pauses and waits for that script to download and execute. This is why script placement in HTML has a measurable impact on how fast the page becomes visible. As the HTML parses, the browser discovers references to style sheets, JavaScript files, images, and fonts. It sends parallel requests for all of them simultaneously. CSS is render blocking. The browser will not paint anything until the style sheet is applied. Fonts cause invisible text until loaded, a flash of invisible text. Images load asynchronously. The browser must coordinate all these parallel downloads while assembling the page structure in memory. Here is the detail that separates fast sites from slow ones. The critical render path is the minimum sequence of steps the browser must complete before any pixel appears on screen. HTML parse to DOM, CSS parse to CSS, both merged into a render tree, layout computed, painting started. Sites that minimize what lives on this path get pixels on screen in under 500 milliseconds. Every unnecessary render blocking resource adds wait time that users feel. Slow pages usually have the same root causes. Render blocking JavaScript and CSS that delay first paint. Large, uncompressed images that saturate the connection. Third-party scripts that add their own DNS lookups and TCP connections. No server-side caching, so every user triggers a fresh database query. And no CDN, so all assets travel from one geography. Each issue adds hundreds of milliseconds that compound into seconds of wait time. From click to painted page, DNS resolves the name to an IP. TCP handshakes open the connection. TLS secures it. HTTP fetches the HTML. The browser parses to DOM. CSS builds the CSS. They merge into a render tree. Layout computes positions. The browser paints pixels. Sub-resources load in parallel. The critical render path determines when you first see anything at all. If web pages now feel like tiny engineering miracles instead of instant magic, that is System Sketch doing its job. Subscribe for weekly system breakdowns in plain English. Next time, we open up GPS and explain how a satellite 20,000 kilometers away knows exactly where you are standing. This is System Sketch.